Welcome to Rubber Duck Engineering. Tonight we are going to add physics to our tower defense game and use it to, I don't know, move things around. Eric, how are you?
Physics. I'm well, thank you. I thought you added physics in the Easy Bake Oven.
I added physics in the Easy Bake Oven and wired it up to just random things. So it's like right now the game just does nonsensical things, but we can try to make it do sensical things.
Yeah, last week we wired up multiple agents to path, and we took our floating point universe and we reduced it down to an integer grid, and then we fought with A star for a little while. And I don't think we actually got A star working on stream.
On the stream we did not, but after the show, if you look in the commit history, you'll see that we went through 3 different A-star algorithms.
Yeah,
and eventually got one that did what we wanted.
Well, I actually don't think it ended up. Many of the issues did not end up being the A-star algorithm per se.
None of them were the A-star algorithm. It was all just us trying to hold it like backwards and upside down. And what we eventually did, which was super useful, is we created a visualization of the nav grid. So we basically put an overlay over the game that showed a green box for what we thought was navigable and a red box for what we thought was not navigable. And then we found out that our nav grid was all wrong, and that's why nothing worked.
In fact, I could probably show that. I'm having the app launch now, and then we can head to the code machine. Are you going to give us a tour of the code?
Oh, sure. It can be really quick. We also had one giant file last week. I just broke it up into 4 different files, so we wouldn't be just like scrolling around forever trying to find the code. But yeah, I'm happy to give the tour if you want to pull up the code machine.
How do I make it? How do I make it go? Well, oh, I see. I have to change the layout. There we go. It was already on the stream. High tech here. Yeah, it's so funny how these projects work out. Like sometimes I go do a lot in the Easy Bake Oven, and sometimes you do. You did it all this week. I have not seen the code since last Tuesday.
Yeah, it sounded fun. So main.dart, I just stripped it down to just literally be the main.
Okay.
And then app.dart is where I put all the widgets. There's nothing interesting in here for this game. It's just, a page that shoves the game widget in the middle of the screen.
Sure, makes sense. This is all the Flutter integration.
Yeah. And then game is where all the interesting stuff is. Mm-hmm. So this is where all of the components are and where the actual game ref is. We'll probably spend most of the time in this file. So we can look at the other files. So geometry, I just put our basic int in the geometry.dart file.
Geometry.dart.
I just put the int rect and I size in here, so we didn't have to look at them anymore.
Okay.
And then navgrid is where I put all the navgrid code.
And you deleted a bunch of stuff.
Yeah, so we had reused the grid class from a previous project that we had done, which had a very fancy grid. And so I just made a much, much simpler one. So I just used a, uint 8 list and then just have get and set bools in it. It just made it much, much simpler.
Okay.
But other than that, I didn't really touch the main logic.
I see. You got rid of the templating, basically. It's mostly what you did.
I got rid of the templating, and we had a fancy indexing class. I just stuck down and just say index X and Y. It's fine.
Okay. Great. So I guess we should show it if we restart and then load her up. This is where you've left us.
Yeah. So they're all those red dots. They're trying to get to the orange dot down at the bottom. And there's a bunch of problems. So like one of the main problems is they keep going faster and faster and faster because it is attracted there with some compelling force that just drives them there. And so they overshoot because they have mass. Because once they get there, they like try to turn on a dime and like, oh wait, I want to go back. And so they sort of end up orbiting the orange dot for a little while. And then like somehow friction or something else in the physics engine slows them down. So they will eventually cluster around the orange dot. And then some of them get stuck. So the ones that so you see there, one in the sort of middle got stuck between 2 blocks. And so I thought maybe it would be neat to try, first of all, to fix the dynamics so they don't go orbit the end state, but also to try to detect the stuck state and then use the pathing algorithm to get out of the stuck state. So sort of combine the physics-based motion with a pathing-based motion. Like somehow detect that oh, I'm not making enough progress right now because I'm stuck. Let me try to figure out a way to actually get there.
So I have a lot of thoughts, maybe thoughts and feelings.
Yeah, I'd love to hear your thoughts and feelings.
I'm not sure you want to use physics for this. I don't know that I'm aware of a game that uses physics for this. I'm sure there are, since there are infinite games. But that's okay though. So a few things we could easily add to get rid of the issues we see here. One of which is that we could add a braking behavior, right? Something that looked at the distance, looked at our current speed, and decided that we should be braking instead of accelerating.
Yeah, right now the force is very simple. It just like aims at the target and just applies a constant force in that direction without any regard for the distance.
We could trivially add the waypointing behavior for like right now you always quest at the target. If you just quested after the waypoints, you
wouldn't get stuck.
You would never get stuck. Yeah.
Well, can I back up and address the first thought that you raised?
Sure.
So the first thought you said is why physics. So when we got the pathing to work, they look so the motion of the objects looks so mechanical because they would go down these exact lines and then like make exact right turns and then go exactly diagonal, and I don't know, it looks so mechanical. And so what I was looking for from the physics is some sort of like smoothing to this thing, so that when they turn, because they have mass and they have momentum, that they sort of turn in a sort of like rounded way, and then they all take slightly different paths. And then I wanted them to not bump into each other, because when they were just pathing, they didn't know about each other, and so they would just like all stack on top of each other. And so with physics, because they are each body, they can't exist in the same space. So those are the problems I was trying to solve by bringing in physics into the equation.
Yeah, and I think the games that I think of, like the RTS games you were talking about last week, I think just solve these things in different ways. They, instead of like bringing out the physics hammer, they like break the problem down into like.
They try to like solve each of those problems individually. Like, oh, okay, I shouldn't get too close, so let me add something to my thing.
Yeah, I think so. So this.
Yeah, but the other thing I want to do is in like an RTS game, if you like select a whole bunch of units and you go say walk over here, they'll end up walking in this formation, or they'll like. Whereas in this, they were all bunching up against each other because they were all trying to like go down the pie slice to get to the center of the pizza, right?
So that actually could be really interesting if we just simply could click to change the thing they were questing towards.
We could do that. Yeah, and I think maybe we could add like a repelling force between them, so that if they got too close to each other, they would want to not bunch up too tightly.
Oh, because it's too bunched for your taste?
Yeah, I mean, they seem like they're, I don't know. I mean, it's an artistic choice, but if they were like, I sort of felt like they should be like arm's length away from each other or something, because that's like a comfortable distance for human beings.
Right. I think I would like to take a yes and attitude here, and we should just see where this goes, see where this takes us. So we have a whole bunch of problems we can solve. Which one did you want to tackle first?
Oh, I think we should do your idea of click to move the objective. I think that sounds super neat.
So the objective here,
the objective is just
have a pointer to it.
It hangs off the game object, so there's just a component for it. So I think if you add an input handler to the objective, you could have it relocate itself based on the input.
Oh, I don't know anything about it.
Yeah, so Flame. So we're using Flame as the game engine for this, and so Flame is super into mix-ins. So there's going to be like an input handling mix-in that we need to add, which I can go look up for you if you like.
Inputs.
Something. I can look it up. For Flame.
Yeah, I don't have a browser window open at the moment.
Gesture input. So there's keyboard input and gestures input.
Gesture input.
So you say with tap detector, because it's built on Flutter, of course. So they have all of our favorite gestures, and then light bulb should tell you what you want to implement. If you go click on the red squiggly for tap detector, light bulb will show up and tell you what's missing. Yeah, light bulb is there on line 14.
It doesn't implement game. Tap detector only goes into games.
Oh, it does? Oh yeah, it's for game. Okay, fine. So you say it goes on game, I guess.
I totally did this in a different Flame game. I just don't have it handy. so you're supposed to do a tap detector on this.
Mhm.
Okay.
And then the function you override is on tap.
On tap. Okay. Is it on tap or is it one of the other overrides? There's like on tap down, on tap up.
What is the squiggly telling you there? No, the one on line 182. Don't override a method. Oh, okay.
Oh, that's fine.
Oh, you might want on tap up. I think on tap up will give you the details, which you're going to want.
On tap. Okay. And I think this, it doesn't return a void. Okay. And so we're going to want info dot position.
It's called event position dot game.
Game. Okay.
I think that'll give you the position and game coordinates. And this thing already knows about the objective.
So this would just be objective dot is just position.
I believe so.
Or say any set state or anything because it's updating every.
Oh, I think we say objective dot center because you want to center the objective. Yep. I don't know what that'll do, but we can try. Try to click, see if it'll move the objective.
Oh.
Oh, and they get excited. They get excited.
Okay.
It's just like Charlie Brown with the football, right? So like they're all going to get the football. You're like, nope, football's over here now.
All right. I think we could trivially add some braking behavior.
One of our viewers has said hello to you, Eric.
Oh.
I feel left out. You don't want to say hi to me?
Hi, Adam.
Thanks, Eric. I appreciate it. I think we need to work on the force equation because this force equation is no good. It's causing them, like it's totally disregarding the distance.
Yeah. So this seems straightforward to do.
Good morning. Hope you're enjoying the show. It is 7:42 here in the Pacific time zone.
So 1942, but yeah. I don't know. Does India use 24-hour time?
Thank you.
I always figured the States was the only place that used 12-hour time.
Oh, that could be. You had it. It was right there. Just scroll up a little bit. Yep, keep going.
I assume it's in objective?
No, it's in all of the attacker component.
Oh, that's right. The attackers. They're here. Yep. Okay. Attacker.
So they have a bunch of waypoint code that isn't used
right now. So force, normalize, scale, speed. Okay. So, like, they want to do things like, whoa, hello. Distance to objective. Wanna current speed divide. We want to like calculate current braking distance.
Oh, so you're thinking about like in the Expanse when they fly their spaceship at like full speed 1G towards where they're going, and then halfway there they flip around and they decelerate at 1G.
Sure. I'm not.
Oh, sorry. I got super into the TV show called The Expanse, where it's like a sci-fi show set in space, but the physics is supposed to be at least plausibly realistic, and so they don't like in a lot of sci-fi shows like the ships just have fake gravity or whatever, so they can be filmed. In this show, they don't get gravity except by actually accelerating, but they have nuclear powered rockets, and so their rockets can accelerate at 1G for arbitrary lengths of time. And so the way they get around the solar system is they accelerate at 1G until they get halfway to where they're going. Then they like pause, flip the spaceship around, and they decelerate at 1G. So by the time they get to where they're going, they're at 0 velocity. Apparently India uses 12-hour clocks.
Oh.
Oh, at airports and railway stations use 24-hour clocks. That makes sense because people are like changing time zones and they could possibly be confused about whether it's the morning or the evening.
Linear velocity, sure. Magnitude. How do I figure out what my linear? I want to know what my speed is from this. I don't know what this body class does.
Linear velocity should be a vector 2.
But I want to know what's the length of that. Vector 2 is.
I do like norm. I can try to jump in here with you.
The braking distance would be the final braking. Oh, so do we have a max speed?
No, it would just keep going as fast as it could forever.
What is this? I see. So speed. Braking speed is equal to speed. So final braking distance would be.
When you say, well, okay, I'll let you go. I'm not entirely sure what you're calculating here.
I wrote out my pseudocode and now I'm filling it in. Who says my pseudocode is any good? I'm trying to get to this equation here. If our braking distance, if our time to brake is greater than our time to object, we should be braking.
Oh, I see.
Otherwise, we accelerate. Right? It's sort of like the bimodal. You're just always using the engine. There's no fuel that you're applying here. So,
okay.
But we have to calculate these, right? If
the braking speed is going to be something, yeah, I'm not sure how you're going to do this, but it'd be interesting.
Like, I don't know if this will be right, but we'll see what the feel is. And so then this is the. Oh, this is the. This force is what.
Oh, it's just length. Is the.
This is not distance to objective. This is
vector to objective. Is it possible to write an OS using Dart? It depends what you mean by an OS. Like, you could definitely write parts of an OS. Like, I don't think you would really want to write your kernel in Dart, but you could write all of your user space in Dart. That would be a totally sensible thing to do. I think Microsoft had a project a while back called Midori or something like that, where they're trying to write all of user space for an operating system in, it wasn't C#, but it was a variant of C#. And so it's definitely a plausible thing you could do.
Wasn't it like Dahlia OS or something? Maybe I'm getting the name wrong, but there's some, somebody's hobby OS that like is all written in Dart, or the user interface.
Do you want me to look for it? Dahlia OS?
It's something like that, because I've seen it, because they of course also have a web deployment, because you can. Somebody's written a user interface like a window manager and all in Dart.
Okay. Oh, Dahlia OS.
Did I get the name right?
Whoa, their website is beautiful.
Current speed, current braking distance.
Cool. This thing is written in Dart?
I'd have to check. Current. So the braking distance is braking distance equal to.
Oh yeah, it's totally all just it's written in Flutter. That's amazing.
I have to pull it up, but I don't have an easy way to do that. You can share it if you like.
I'll put it in chat.
Okay.
It looks beautiful. I put it in chat. Sorry, I got distracted by that. That was really cool.
Wait, remind me how. Right. So how do I calculate time to brake? This is braking time to brake. Right. So we have a current speed.
Mm-hmm.
There's like an offset from. This is like a solve for the function, right? And we have a linear function. No, it's not a linear function. It's a quadratic function, of acceleration, and we want to know when it intersects 0 or passes 0. Right, so what is that function? That's going to be y is equal to tx, like your distance.
It's just fascinating that you're watching your problem-solving approach. I would never have even thought about solving the problem this way.
Well, how would you solve it?
I would solve it by just specifying a series of forces that would have as an invariant that it would reach the destination at velocity 0.
Okay. I'm happy to... I don't know what you mean by that.
So like I would calculate the potential energy.
Oh.
And then just apply a force that reduces the potential energy at all states. And so that'll basically force it to come down. I guess you have to do the total energy, the kinetic energy plus the potential energy, and then find a force that will reduce the total of those two. And then in the end, in order to have 0 energy, it must be at the bottom of the potential well and also at 0 velocity.
So kinetic energy, this is equal to velocity times mass?
1/2 velocity mass times velocity squared.
And what's potential? This is 1/2?
That has to do with the distance to the objective.
Oh.
The potential energy.
You're thinking about the forces being like a gravity. 1/2.
Yeah, I'm just pulling up on Wikipedia here.
If I just hold on for a second, I can pull up a browser. I have one here somewhere.
Yeah, potential energy for gravitational forces between two bodies.
Okay.
Yeah, so you got Wikipedia.
What do you want?
Here. I'll just go to potential energy article on Wikipedia.
So
and scroll down
thing. What did you say? What do you want to show us here?
I'm just going to scroll down to potential energy for gravitational force between two bodies. So that's the equation I would use. So minus some constant, the mass of the two bodies divided by r. So basically minus 1 over r.
Okay. So one difficulty with this is that with obstacles in the way, the distance is not just.
Yeah, so I think we should do that separately. But what I was thinking about doing that is like somehow detecting, oh, I'm stuck. I'm not able to make progress.
Sure.
Now let me do an A* path and then go to some intermediate point using the same equation.
Okay. Oh, I see. Okay. Yep, makes sense. Are you still going to want to stop at those intermediate points, or do you going to want to carry through velocity?
I don't really want to stop. That sounds silly. That would be like doot, doot, doot.
Yeah, so you're going to end up wanting to carry through velocity, but that's fine. That's an easy thing to do, like to change your behavior. Okay, so let's take a look at. All right, so am I continuing down this path, or are we trying our potential energy here?
Well, it's up to you. I think either are viable. What makes the most sense to you?
I don't know. I'm going to keep typing breaking code because that was where my brain was.
Okay, that sounds cool.
All right, distance object, current speed. Well, this was the thing that I didn't think about how to, because your time to break, you're trying to solve for, t, right? T is equal to divided by accelerate.
I think this might be easier if you just consider a max speed.
Okay.
Yeah. So your question is, if you apply a force in the opposite direction of a certain size, how long does it take you to get to zero?
Correct.
Okay.
Yeah. So this is force.
Right. So we need to figure out like. So I would just start with F equals ma. This was when I took physics in high school. My physics teacher used to get really excited. He used to call it, well, I shouldn't say what he used to call it, but he loved this equation. Okay.
Okay.
So then velocity, we have to integrate this, right? Velocity equals mass times, what's the,
We're going back like 30 years, 20 something years.
integrate force over time. Yes. Internet, tell me the answer. Impulse. Okay, this looks plausible. All right, so we should just call this the thrust, right? Like instead of speed, we should call this thrust.
Okay. I have no idea if this is correct. That's fine.
Okay.
So if this is true,
then the time to break is. So you need time to object.
we're missing our current speed here.
We need to compute time to object. So we need our distance to object is going to be distance to object, distance to objective divided by current speed.
This is also time to break. Also needs this in here too. We're missing a.
It doesn't. Oh, does it? Oh, like the speed that we're going now.
Yeah, there needs to be a. I don't know where it gets added, but here it's equal to.
I feel like we're not doing this right, but anyway, distance to object divided by the current speed. That seems legit.
All right, so time is equal to. So this is distance plus velocity.
So this ends up
distance minus
time, right?
Velocity. Yeah.
Yeah, it just ended up here.
Oh, you already did it? Are you sure that's where it goes?
That's all right, because the time factors out. But the time is in both here, right? So this is just thrust squared plus. I mean, I don't know if any of these equations are right, but we're sort of following along. Well, our current thought process, it ends up like that, right? Just thrust squared and velocity.
Okay. Yeah, we can try it. It's gonna look. Okay. Did we end up have thingies in here? I can't remember. I'm writing too many different languages, man. Okay. This is distance to objective.
So we keep this, right? This part is good. And then all we do is we apply our
Which direction?
Yeah.
Yeah, I was trying to write this. I was optimizing too early, but I was trying to write this with the idea that you could have different braking forces versus accelerating forces.
Okay, but our engine on our particle is so strong, and we're just going to flip it around like on the expanse. Vector to objective.
I think you mean apply force.
I remember this energy wave.
I don't think this is what you mean.
What did I do wrong? Time to break is greater than time to objective, then we can go forward. Otherwise, we have to do this. What did I do wrong?
If time to break. No, you had those correct before, but
Okay.
This is breaking. Okay, so we're scaling the force.
You can also just consider the units. Speed is meters per second, and acceleration is meters per second per second. And you're looking for an answer in seconds. So I think he's telling us we have way too many meters, right? Because acceleration squared is going to be meters squared per second squared. Okay, James is telling us that we screwed up our units. So
I expect we did. Can we also try this? Because
we'll try it. And James, we do not ignore you. We will go back and fix the units.
Yeah,
I'm curious about what disaster is going to occur.
I want to see my little things explode here.
Okay, they're going. Slow down. Not happening.
Are they ever slowing down?
I think James is like an actual engineer who knows physics and can tell us.
This doesn't seem any different than before.
True. Maybe that's a sign. Okay, let's look at our units. I think this is a good. So current speed is in meters per second.
Mm-hmm.
I'll do this like meters per second. Okay. Thrust is in also in meters per second per second. So thrust squared is going to be, this is way off. Thrust squared cannot be what we want.
What is thrust here? Is it force?
Thrust is like a unit of force. Like how strong is our engine? James, can you save us? What is the proper equation that we're supposed to do? The breaking time.
How we're gonna phone a friend?
Phone a friend. It's a collaborative show. We could try to struggle through it here.
Okay, I think I'm so. Okay, what is?
Well, when we get to the equation for speed, like we know what the velocity equation is, right? So like speed, our speed is going to be time. It's going to be thrust times
our speed at time. Our speed at time t.
Yeah, our speed at time t. It's going to be our speed at time 0 plus thrust times time.
Because thrust is our rate of acceleration.
Right, it's really the integral.
So we definitely don't need a square thrust here then.
Right, so let's just start back at F equals ma. F equals ma. Okay. I know that one is right. That's as far as I've gotten. So now we need to do some integration to get to this, right? Thrust times time. If this were just regular velocity, this would be right. But this is not quite right.
What?
Okay, this is for the breaking time equation. If thrust is mass times acceleration, and the mass is unit, then the acceleration time will give you a speed. Acceleration times time will give you a speed. Yeah, we're there with you.
I think I'm still lost as to what are the units. What units are you trying to assign to thrust? This is rate of acceleration. Is there a mass component?
Well, let's assume unit mass for simplicity.
Okay.
This is meters per second squared.
All right, so this is acceleration.
That's acceleration. Yes.
Okay.
Okay, it's giving us more hints. If you want to square time to integrate it over a period, you will get distance. Oh, that seems useful. So let's square time. So we need a square root. There's going to be a square root involved. Oh, okay. I think I got what he's saying. He's saying that it's going to be distance is going to be velocity times time, and then plus acceleration times time over 2. That's what Copilot told me.
Why is the over 2?
Because we integrated something. I don't know. You want to square time to integrate it over a period of time to get distance. Yes. Okay. Where did the 2 come from? The 2 is so that when we differentiate, we get acceleration. Like let's differentiate this equation, okay? I'm excited about this equation. Let's differentiate this equation with respect to time. So then we'll get velocity. This term will go away because it's not changing. Oh, this term will just be also velocity sub 0, let's say. So this is velocity at t, will be our initial velocity, and then we'll differentiate this with respect to time. This will go away. The power of 2 will come down and cancel out this half. So this looks legit. If we differentiate this with respect to time again, we'll get acceleration.
Are you saying this is... I'm so confused by that over 2, but okay.
This equation looks legit to me. Oh, I can explain the over 2.
And what parts are over 2? The whole thing, or just
this part here?
All right, so can we put some in parentheses here, like this?
Yeah. Go for it.
It really times 1/2, but yeah, go ahead.
Yeah. Mm-hmm. So this equation, if you differentiate this equation with respect to t, you get this equation. Let's just make these a's, right? Oops. Because this t drops out when you take the differential, and this t squared becomes the differential of t squared is 1/2 t, 2t, yeah. And so that's why you have the half here. And then if you differentiate this with respect to time, you get to acceleration equals acceleration, which seems legit.
Okay. Okay. So I'm sorry. So our distance at time t. But
right. So now we see this
time.
Right. So we need to solve this equation for t. So now let's solve this equation for t. Okay. So to solve for t, so let's call this d. Okay. How are we going to solve this for t?
Well, we're going to start moving terms. We're going to do 2d is equal to v times t plus a times t times t.
There's going to be a 2 here.
We're going to divide out t. Well, we don't have 2 on this side. Oh, I see. You're right. 2b. Yep. We're going to divide out t on this side.
Wait. We need to use the quadratic equation. Right?
We need like a sound effect. Deploy the quadratic equation.
Okay, so let's get this into the form where we can apply the quadratic equation. Oops.
we named this. Did we name it physics? We did name it physics.
We did name it physics.
We are correctly doing physics.
We are correctly doing physics. Oh, okay, I'm going to just put this in a form where I can apply the quadratic equation.
Oh, okay. We're long overdue.
For the quadratic equation?
No, we're long overdue for the banner.
No, I know the quadratic equation. It's my friend. Okay.
The quadratic equation is a plus b equals a squared.
Okay, let's look at the quadratic equation.
No, that's the...
Yeah, here we go.
This was last century, man.
No, the quadratic equation is legit. Okay, so you start out with the form. Okay, we're going to have some like letter collisions here. We're going to have to rename our variables. So we start out with that form, and then we get the quadratic equation. It's given by this.
Oh my goodness.
Boom. Okay. This is episode 100 and something, and we finally got to the quadratic equation. This is great. Okay, this is we're missing the little thing here. Deploy the quadratic equation. Okay, but we have too many A's. Like, I'm going to rename these variables, okay? Because we have A's and stuff over here. So we're going to use R, S, and T.
Does acceleration have a different constant?
Well, I just don't want to get confused because RA is really A over 2, right? That's fine. We just need to pick different letters so we don't get confused.
Okay.
So I'm going to pick K. So A is going to be K.
Why don't we just do DEF?
Oh, D, E, F? Okay. D.
Oh, except we already are using D. Okay, we're going to have to EFG.
Okay, ready? E, F, G. E. That's not confusing at all because E is a constant. Okay. F. Mangle the quadratic equation. Step 1. I love these little like floating.
We're so off in the crazy weeds.
We're off of the crazy weeds. That's awesome. Okay. And then this is G. The C is becoming G.
Where we're showing the world that we do not remember high school physics.
Oh crap. What was this? This was A, right? So this is E. Okay, we got it.
A squared plus B squared minus C squared. I don't know.
Okay, so what is E equals? E is going to be equal to A over 2. Okay?
Okay.
Okay. And what is F going to be equal to? They said in high school that I would need to use this, and I've never needed to use it until now. So we got that going for us. Okay.
F, if you're watching this and you're asked for the quadratic equation in a SWE interview,
you run away. It's not.
Yeah, that does not match my experience.
Okay. Did I get these right? Oh, is it going to do it?
No, did you just make Copilot do it?
Copilot spit out the mangled quadratic equation. No, but it didn't even do it right. Okay, so let's figure it out. Let's do it right. So minus F is minus V. Okay, plus or minus. This is an amazing Unicode symbol here. Plus or minus. Okay, I'm just going to math.squirt. F squared is V times V. Right? 4 times E. A over 2. We'll get this. And then G is minus D. Okay. You checking me here?
I mean, I see you doing the substitution theoretically correctly.
Theoretically, I was hoping you would check me on the substitution. 2 times E.
A over 2.
A over 2.
So it's just A.
Okay. Okay, let's check the substitution. Okay.
Okay.
Did I do substitution correctly? So F was V. Yep. That looks legit. Plus or minus square root F again was V.
And what's the plus or minus?
Oh, wait, we need a minus here. Because there are two solutions to the quadratic equation, right?
Oh.
We always want the positive one. So we'll just take an absolute value when we're done.
Well, why don't we just plus here?
We'll simplify in a second. I just want to check the substitution that we got it right. So E was A over 2. Okay. Minus G was minus D. Okay. 2 times E. E was A over 2. Okay, good. So we start simplifying?
These are like flashbacks to 1996, man.
I do not know how well I did in this high school class, but I
aced my high school physics class.
Okay, I want to make a copy of this before we start editing it and messing it up. Okay, so this 2 and this 2 cancel out. We're just going to divide by A.
Okay. Go us.
Oh, wait. What is this thing? I'm still dubious of the... Oh. I think it's actually legit. Because I think if you go look at our series of acceleration, velocity, distance equations, like I think if you differentiate distance, you should get velocity, right? And so I think that's actually right. I'm sure some website will tell you. Okay, I'm simplifying these equations.
Distance is equal to no distance.
That's true, but not what we want. Okay, I'm gonna absorb one of those into here. I'm gonna absorb this minus sign into here.
Distance is equal to V times T plus 1/2 A.
Oh,
yeah.
I'm gonna absorb this plus or minus.
Oh, always trust Copilot. By always, I mean never, but yes.
I'm just going to put this over here. Always trust Copilot. No, Copilot produces buggy code. It's like plausible code, but you really have to code review it.
Yeah, you do.
We
were having this conversation at the water cooler at work today, not literally, the figurative water cooler, about how Copilot's going to change our jobs.
Oh, James agrees with us. Okay, so here we go. So I think we got it. So now we just need to translate this back into actual code. Okay. We started today's episode. I had no conception that we'd be busting out the
No,
quadratic equation.
not at all.
Current speed squared. Acceleration. Distance to objective. Okay. Okay. Minus the velocity, which is also our current speed. Okay. Divided by the acceleration. Okay. We would not have got that equation just by trying random things. We want to take a math.abs here. On the this is abs comes out here.
This is not Python.
This is not Python. Okay, try that.
I was reminded recently that the Python, the filter and the map and the like, all those operations that in Dart are on the list. You're supposed to be breaking by now.
We did something wrong.
I feel like it's accelerated more. Like,
I don't know.
Do I need to restart the whole thing?
Restart the whole thing.
Seems like it's breaking less now.
It's definitely the computer that's wrong. It's not our math.
What? It's like overshooting more now. Okay. So if your time to break, is the force always...
Well, let's check time to objective, though, with our new knowledge of math. Time to objective... Okay, let's solve for time to objective. So the distance, that's just this equation, right? So let's start again.
Okay.
Okay, so our distance is going to be this. Let's just solve this this is with no acceleration. So set the acceleration to 0. Right?
Where's our V0? We need to have a V0.
That's our current speed.
This is wrong. We're also, we missed, right? So we did this here wrong too. We missed our V0.
We're not using this one. We started here. This is what we used.
But where's our
V0 is here.
Oh, okay, you're right. And we don't care about the constant offset, right? Because normally you're x squared plus x, what is it? It's like ax squared plus bx plus c, right? I don't see c in this equation.
Well, c is going to be distance, right? When we go and solve it, it's here.
It's also relative distance. We don't care about the absolute distance.
Right.
Okay, okay, great. So time to objective, we need to solve this for t.
Right, that was right. Because acceleration was 0. So this term dropped out. And then it was just distance. It was divide this by v, right? That was right. Where did we go wrong? I feel like we got wrong.
It's hard to see the wrong through the quadratic equation here.
Okay, here's what I suggest. I suggest we make a single attacker, like go down to one attacker, and then we log the time to break.
All right, so let's... I agree that we should simplify down to area attacker positions, 1, and break.
It's a combination of physics and engineering. No, we're not doing the engineering part.
I'm much more comfortable in the engineering part. The reason why I aced physics class was that my teacher would allow you to bring one sheet of paper with as much written on it as you wanted.
And you wrote really small.
What'd you say?
And you wrote really, really small.
No, I always typed up basically a full recap of all of the notes of the chapter into a single thing, and I printed it out on sheets, and I just distributed them to the class. But I had done it all, so I like remembered the stuff and could do it.
Oh, you sabotage everyone else's studying because they're like, oh, I got the paper from Eric. I don't need to study this.
I guess. I think I was learning LaTeX at the time.
Oh, what a great idea. We could change the color of the attacker when they start breaking. That's an excellent suggestion.
That's like cheating, but yes.
It's not like cheating. That's like amazing. Okay, so let's go up here.
I think there's a visual debugging component of games that is not.
Breaking paint. Which color should we be breaking? Pink.
There's like a visual debugging point of games that is not something I've internalized yet.
I think we could just say paint equals breaking paint, and that'll do it. And then here we'll say paint equals
accelerating paint.
Sure. Accelerated paint. Okay, let's try that.
There's a visual debugging component of games that I don't do automatically. So what's it going to change to?
Pink. Maybe pink is too subtle. How about green?
I don't notice it changing.
The colors are too similar. Let's try green. I switched it to green. Yeah, the equivalent of printf debugging in graphics programming, exactly. Oh, well, that was a bad one. It got stuck.
Roll the dice again.
Go, little guy. You can do it.
I don't see any.
No, it's clearly never switching over. But it's fine. Can we look at the log?
Well, logs. Debug console.
It's going down. Oh, then it's going up and then down.
Oh. It occurs to me that
we've picked the wrong. What?
I wonder if we're thinking about the time and like velocity relative to like the angle. Right? We're not considering angle. We could be if our speed is we're just taking the distance of our speed.
Yeah, but we have a bigger problem, which is we're never breaking. I think you're right. We'll have to consider angle at some point.
Why are we never breaking?
Why are we never breaking? So what's happening is as we're going faster and faster, this number is going down. Can you log the current speed also? Because I'm curious about that.
Sure.
Like
you can have it.
Time to break. And I also want to say time to objective. Current speed. Current speed.
We're gonna have to do a lot in the Easy Bake Oven this week.
Oh, that's fine. I busting out the quadratic equation on the show is making me very happy, even though it didn't work. Okay, let's. I'm curious what that logs. Okay, so time to break is decreasing. Oh, our current speed is. Can you just pause it so I can read what it's saying?
Mm-hmm.
Okay, so in the end of this log, the current speed is increasing, and our time to break is decreasing. That relationship seems bad. Our time to objective is decreasing, which is good.
Time to break is current speed times current speed. Why is it current speed?
Because that's what the quadratic equation told us. It's f squared, which is the linear term.
Okay. Current speed times current speed plus.
Let's try that.
And why is it 2 instead of, because we simplified out? Because E. Okay.
Because there was the E had a half in it. Yeah. I wonder if that sign was wrong. But try this.
Okay. Nan.
Okay. Well, I guess not. Oops. Why do we get nan?
I have no idea. So I'm sorry. Our time to break. We would expect our time to break to be going up as we go faster.
Right.
We're both getting closer and we're going faster.
Oh, I see. So maybe the going faster is dominating. The getting closer is dominating.
I mean, we could isolate this, right? We could just not apply the force. Right. If we remove this line.
Well, then we won't go anywhere.
Yeah.
But we can say if current speed is greater than what is it? Current speed is greater than 1, and return. So only apply the force for small speeds.
I see. This is we've added a max speed here that we're not accounting for in our equations, but
It's also possible this paint assignment isn't working.
So time to break is going down. Time to objective is going down. And the force, or the acceleration, obviously, this makes sense, right? But time to break is going down as we get closer.
The time to break should be constant. Like, why does the time to break have to do with the distance at all? Maybe we need to set the distance to 0.
Time to break totally has to do with the distance.
Oh, because the closer you are, the less time you need to break. That makes sense. So we're expecting, is the time to objective going down faster than the time to break? It's like, is it 40? Yeah, it's definitely going down faster. So this will eventually break.
In 31 seconds.
I'm going to put a print for breaking.
Oh no, it's stuck. I mean, we know it's not breaking, right? We can also remove the obstacles, by the way.
Oh, okay, I'll remove the obstacles.
And maybe we could set our max speed to 5 or something.
Okay. I removed all the obstacles.
So like here, it should be breaking.
No, not quite yet. It should be breaking. It's never breaking, right? The time to objective and the time to break never cross. That doesn't seem right.
So, okay. And how is the time to objective defined? Is this the plus or minus? Like, do we want...
It's possible. So let's try the other. Let's try it. I switched the plus or minus around. But I don't think that's going to matter. Whoa. It was the plus or minus. Because now it's going to switch over.
Solution in the quadratic equation?
We picked the wrong solution in the quadratic equation. All right, so now it should be breaking. It's breaking. Oh, that plus or minus for the quadratic equation.
But we're still going to overshoot.
Why are we overshooting? Oh, because we have our max speed and everything. Let's take the max speed out of the thing now.
Okay.
Okay.
Like, so... Whoa. Why is it like constantly. It's like giving itself its own max speed. It's going to perfectly arrive at it.
It's just like riding the edge between. Okay, it's like thrusting and braking, just so it hits exactly.
Oh, it sped off into the sunset because it overshot? Like, I don't understand. Its time to brake is now. What? Current speed.
Maybe to compute both.
It's going to space.
Okay, we're sort of at the end of the episode. I think we should just make it spam a ton of attackers, and like,
and they can all go to space.
they can make them all go to space. Yeah.
Okay.
So the other way to do this is you can just compute one of these expanse style orbits, and you say, I want it to take X amount of time to get there, right? Where X is whatever, like, and then you can say,
well,
you can compute
we
like
have
what
a
is
max speed in real world, right? We don't have max speed in our equation.
that's true.
Also, where is it going? Why is it not? Is it speed negative or something? Like, what? It's braking. Oh, I see. It's braking faster and faster.
It's braking real hard.
And it's braking faster and faster. So the signs are wrong here.
So we can take away this absolute value is probably what's messing us up. I think we should rerun it. I added a bunch of things. It's going to be entertaining, and
then we're gonna scene.
Oh, you should rerun it. It should be 50 things.
I did.
Here's some information.
I don't know why.
Did I not add?
Did you not add?
Oh, general attacker position 50. I put the 50 in the wrong place. I put the 50.
Whoa, it went off. I think it gets into negative braking territory.
Look at him go.
I don't understand why it's trying to hold a.
There's still something wrong. It's still messed up. But they're flashing like we selected red and green, which is not good for people who are colorblind. We should have selected a different color. The people who are colorblind can't tell which ones are braking, which ones are accelerating. Yeah, James thinks it's perfect. So I think it's perfect too. I agree with you, James.
But it's once it gets into negative territory.
And then it's all messed up. Then it keeps trying to
it tries to brake.
It tries to go away from the objective as fast as possible. We shouldn't allow you to braking to increase your velocity. Because if braking is like increasing your velocity, something is very wrong.
Huh. Well, I think it is what it is.
Oh, we could brake along the velocity vector. We should brake along the velocity vector, not along the distance to objective vector.
Oh, interesting. That we pick either the like forward velocity. It's not a. Yeah, we don't want to scale the.
Can we try that?
Flaws. I appreciate the vote of confidence, James.
Okay, so when we're braking, we want to take our vector to our velocity vector.
Where'd we go?
Where's our velocity vector? Linear velocity.
I wish there was like a quick way to get to you.
Okay.
So what did you change?
I haven't changed anything yet, but I was going to change this.
Oh, interesting. So braking is different from accelerating in that it just reduces your velocity vector.
Correct. You accelerate on the opposite of your velocity
Doesn't
vector.
this need to be negative acceleration?
That's negative acceleration.
Right? Like a negative there?
Yeah.
Okay.
All right, try that. I realize we're over time, but I'm I'm entertained.
Are you not entertained? Why is it? I still don't understand why it does the.
Because there's something wrong with our math.
Now they're like zombies here.
Well, they're gonna like arrive at time infinity or something. I did normalize because I didn't want to mutate. So normalize. Well, let me just take this off the screen so you can see what's going on.
I mean, this worked.
It worked. Yeah. Normalize will mutate the underlying vector. Normalized will return a copy that is the
Yeah.
So I didn't want to mutate the actual linear velocity.
Every framework does this funky.
Yeah.
I was reading a framework the other day that that uses a trailing underbar to do the like local modification, and this one does different names, but it's all subtle. Like, does it self modify or does it return a copy?
Well, this was fun, Eric. I really enjoyed busting out the quadratic equation and fulfilling the prophecy of like high school mathematics of actually needing to know the quadratic equation.
Now,
of course, I didn't actually need to know it because I could look it up on Wikipedia, but I needed to know that it existed.
I kind of want to go find my physics is fun Word documents containing all of the contents for the final exam.
We probably have all these equations in there, and we could have just taken them from there.
Anyways, good to see you as always. Thanks everybody for coming by, and for those of you watching tomorrow, have a good week.
Yeah, see you next week.